here we do have an equation defining the relation between input and output. And then we have tried to start sketching the impulse response, right? And so on. But very soon you may, one way or the other or another, you will realize that the impulse response consists of only two non-zero samples. These are the only two non-zero samples, okay? One is located right at time zero. So if this is time, we have time zero. Now the impulse response h at time zero, it equals to 1 divided by t. And at time 1, it equal to the negative of that, minus 1 divided by t, where t denotes the sampling period. Okay? Yeah. And everywhere else is 0. 0 everywhere else. Yeah. Only two non-zero samples. So now we may ask a few further questions. Is the system causal? Is this system causal? Yes. Because the impulse response is what? The impulse response is all 0 before time 0. All 0 before time 0, yes, we have checked. It is causal. This satisfies causality. Okay? The first thing first, is the system causal? The answer is yes. And we have drawn the sketch right here for that impulse response. Now, the second question right here. The second question, does the frequency response exist? Does the frequency response exist? Okay, so does the frequency response exist? And we need to ask the question, how about summation of n, of all n, right? Summation of all n, h of n, e to the minus j omega n. Does it exist for all frequency? And the answer is, of course, it exists. This is not even an infinite summation. Is that too quick? This is not even an infinite summation. We have only two non-zero samples, right? So, sure, the frequency response, which is the Fourier transform of the impulse response, if of course it exists at every frequency, because we are not even talking about infinite sum. There's no issue of convergence. You know, the summing two part is actually really h of 0 e to the minus j omega 0 plus h of 1 e to the minus j omega 1. Of course, this converges everywhere. Okay, the z transform converges on the unit circle. Okay, right? So everybody clear, there is no issue of convergence. This is what we call finite impulse response. FIR is always stable. The Fourier transform always exists. Okay? Only two non-zero samples. Of course, there's no issue of summing infinitely many terms. 并没有在做无穷求和啦。所以 Of course, the Fourier transform second question, my answer to the second question, does the frequency response exist? Yes. It exists. It exists. So now we know it exists. Let's plug in the number, shall we? Yeah, plug in the number. We have 1 over t, and this term is just 1, and plus minus 1 over t e to the minus j omega. That's the frequency response, seriously. It's a function of omega now, right? So this expression is correct. Okay? This expression is the frequency response, and then, but the next thing is a bit more tricky. Okay, that's what I really want to show. Is the next thing. Now, all right, this is a complex number. In general, this is complex number. Let's simplify it a bit. So there's a 1 over t factor that can be extracted. So inside we have 1 minus e minus j omega. Looks like that's the result we get. Okay, this is what we call the frequency response, a function of omega. Okay, the next thing is a bit more tricky. Now let's ask about what's the magnitude response and phase response. Seriously, okay, magnitude response we need to put in absolute numbers, right? No, absolute value, 绝对值加上去 right? That's seriously what we mean, frequency response, magnitude response. Okay? Which one do you want to show first? Magnitude or phase? But before I move on, okay, this is one way to derive the frequency response. But let's, before we fill in the details for magnitude and phase, there's another way, solution 2, which is worth mentioning. Yeah. Okay. Remember how this lecture, how we just learned is Z transform. We can also use Z transform. It's useful. Okay. Z transform can be used for derivation of frequency response. Why? Because frequency response is Z transform evaluated on the unit circle. Okay, so let's do that. Solution 2, starting with yn equals to x of n minus xn minus 1 divided by t. Okay, that's in the time domain. So let's take both sides of the equation to the Z domain, applying Z transform to both sides of the equation, shall we? Applying Z transform now. So on the left side, after Z transform, if I use script Z to denote Z transform, okay, 草写 Z, Z transform. Take the Z transform, the result, of course, is YZ, right? By definition, we don't even need to show it at this moment. But now, what's the Z transform of 1 over t? Now, x of n, when we take the Z transform of x, that becomes big X, okay? And there's a property that when we shift in time by one sample in Z transform, that corresponds to 1 unit delay, okay? Which is denoted, as you can easily show, Z inverse, I call this Z inverse, 导数了, Z to the minus 1 power, 1 divided by Z, each way Z. Z inverse, that's the way I call it, Z inverse X of Z. So that's a trick. Do this completely in the Z domain. That's a shift theorem. A shift by one sample to the right, you multiply in front with a Z to the minus 1 power. Okay? Z inverse. So far, so good? Is it clear? It's an important trick. Everybody should know it after taking DSP, all right? So please be sure you know this trick, okay? But then from there, if you can learn this, if you accept this, then this is cool. Then we have 1 over t, then we have 1 minus Z inverse times big X as a function of Z. Then, okay, then what's next? And by definition, Y by definition is equal to the system function times X of Z, right? So then simply, because Y convolution theorem, right? System function times the X, big X equals to big Y. Okay, so then what is the system function? H of Z. Can you tell me? H of Z is E 减掉 Z 负一 1 minus Z inverse divided by big T. Okay, scale by big T. Quickly. And we have all confidence. We have the confidence that this is going to be equal to the Z transform of the impulse response. So do we have the same result? Do we have the same result? Yeah. So that's a kind of a nicer trick I would like to share with you. Just use Z transform, and we will repeatedly come back to this. Okay? Important stuff. Everybody okay? Yeah, this is important. Very nice trick. And this really, H of Z, and then what else? Then what's the frequency response? What's the relation between frequency response and the system function? Frequency response is system function evaluated on the unit circle. Right? So therefore, just simply using this very nice notation, H of EJ omega, already by this notation, 如果够熟练的话, you are sophisticated in this notation. Immediately, by evaluating this system function on the unit circle, you get the frequency response of the system, which is 1 minus E minus J omega divided by T. Do we have the same result? Okay, do we have the same results? We have the same results. Okay. So contemplate, let's contemplate on the two solutions. Okay. Different ways to to reach the same conclusion. Okay, to reach the same conclusion. All right, yeah. So now, with two different ways to reach the conclusion, now we have an expression for, a consistent expression for frequency response. Let's calculate its magnitude and phase. Right? So next thing I would like to go together with you guys is to calculate the frequency, the magnitude and phase. Yeah. To calculate the magnitude and phase. Yes, so this is our frequency response. So this is a bit tricky. So let me just elaborate this expression a little bit. Okay, I'm experienced now. What is e to the something, e to the j something, using Euler's formula, 尤拉公式, Euler's formula. E to the something, that thing is cosine omega. And there's a minus sign, there's a minus sign, so I think this is j sine omega right here. But now instead of directly put the absolute value right there, our goal is to calculate magnitude and phase, right? But here I'm experienced, okay. What is 1 minus cosine? 1 minus cosine omega is what? Does it equal to 2 sine squared or something? Have you learned this in high school? 2 sine square omega divided by 2. I think that's the answer. But then what is sine? Sine omega can also be expressed as 2 sine omega divided by 2 cosine omega divided by 2. Why do I do that? Okay, the reason will become clearer. Okay, so I'm going to use these two identities, trigonometric identities, 三角恒等式. They turn out to be useful. They turn out to be useful. So if we just further proceed with our calculation, 1 over t, so we copy everything, 1 over t, and now it seems that we have a factor of 2 cosine, 2 sine. We have a factor that can be pulled out, right? And then inside, we have sine what? Plus j cosine. Yes? So miraculously, this is what we have. Yeah? So far, so good? So 1 over t is still here. 2 sine omega divided by 2. But then what is here? This is a point on the unit circle, actually. This is just some very nice trick regarding this very exercise. Okay, not that important, but hold on, just bear with me. Bear with me. So what is this? I can write this as e to the j. Actually, it's pi divided by 2 minus omega divided by 2, right? Because ej something is cosine plus j sine, but pi over 2, that's 90 degrees, 90度减它正弦变余弦，余弦变正弦 Sine becomes cosine, cosine becomes sine. Okay, so I'm familiar with this example. That's why I can make this tricky derivation. Not that important. Okay, so this is great. So now we have more or less, this becomes the magnitude, but not really, not quite. But that becomes the phase. because this thing here is great. This is real, right? This function as a function of omega is real. And this as a function of omega, the phase, is each exactly in the correct form that we want. This format is exactly what we want. E to the j something, that thing is a fixed spectrum, right? And in front we have a real thing. Good. That roughly speaking, that's the magnitude. Okay. Yeah. So that's kind of a trick. First, you don't absolutely need to follow me. Okay. You can try to just extract the phase directly from here. That's all right too. Okay. But this is just because I'm experienced. This is a very nice example, classic example, 非常经典的 example 啊。So now we are ready to plot the magnitude response and the phase response. Okay, so the magnitude response is supposedly should be the absolute value of our frequency response. It's going to look like what? The result is 1 over T2 sine 那个东西啊。1 over T2 sine omega divided by 2. So how about when it goes to pi? That's the question. Okay? When it equals to 0, the magnitude equals to 0, right? And then it's basically going to reach to 2 divided by t, I think. Am I right? Yeah. 1 over t 2 times sine omega divided by 2. Okay? So it's 0 for frequency, 0 for DC. The gain is 0 for DC. And the gain reaches its maximum at Nyquist. That's really seriously, that's what we mean, okay? The magnitude response of this system has a 0 gain at DC and maximum gain at the highest frequency, which is corresponds to Nyquist. Okay? Pi is Nyquist. Okay? So that's the magnitude response. And how about the phase response? The phase response is equal to what? 90度 pi divided by 2 minus what? Minus omega divided by 2, right? Omega divided by 2. So it's a straight line. The frequency response is a straight line. No, the phase response is a straight line, okay? Which equals to pi divided by 2, and then straight line zero with a slope, and it's a straight line equals to 0 at Nyquist. So that's my solution, my quick sketch. Okay, we have a system, a discrete time system. Now we can talk about magnitude response and phase response. This is one example. Yeah. One example. Okay. Yeah. All right. Any comment right here? Yeah. Is everything clear? So this is the very first system that we look at together, okay? Very first systems we look at together. I've shown you how to derive the system function and frequency response more quickly, perhaps in the Z domain. Z transform is useful, okay? Please, understand that. Z transform is helpful. And then later, that trick is not absolutely important, but here, with that trick, I was able to show the magnitude with 0 gain and maximum gain, a straight line for the phase phase response. Okay, so I do have a remark. Okay, any questions so far? Any question, comment regarding this example? Does it make sense? Is it making sense? Is it making sense to you that DC gain is 0? DC gain is 0. Okay, does it make sense? Does it make sense? DC gain. Let's contemplate the result. Okay, the DC gain is 0. Is it making sense? I like this question. Is it making sense? Yeah. I think it makes sense because when we have DC and we are subtracting the previous example, previous sample from the current sample, the result comes out 0. Okay, everywhere. So the gain is 0. Okay, in that regard, it makes sense. Okay. But then I want to share with you that I call this system numerical differentiation. 数值微分 This is the way I would call it. Now, this system can be called numerical differentiation. Why? Anybody want to guess why? Why am I calling it numerical differentiation? 数值微分 in what sense? In what sense do we call the system numerical differentiation? Differentiation can only happen in continuous time, right? But in discrete time, we can approximate it. In discrete time, we can approximate time derivative by just subtraction, just delta x divided by delta t. That's what I mean. Do you notice that this is delta x, right? The change, the amount of change in x after one sample. When time proceeds from n to n minus 1, what's the change? So this, in a sense, this is the amount of change in x. Okay, divided by this little short time t, right? Sampling period is a short time. Okay. So this is really, the meaning is delta x divided by delta t. Yeah. That's what the system actually is doing. So again, to contemplate on our result, what this system does, y of n equals to x n minus the previous sample, that's a change, right? That's a change, and t is the amount of change in time. So in that regard, this is like delta x divided by delta t, something like that. Something like that. And we know that when delta t approaches 0, then is essentially calculating a numerical calculation of differentiation, 变成数值的微分的数值逼近了啊。Is that clear? Does that make sense? Is it making sense? All right. So if it makes sense, delta x, delta t. This is just before we know that. Note that limit delta t approaches 0, delta x, delta t is basically the definition of dx dt. So that's why in this sense, I'm calling the system numerical differentiator. So if this makes sense, then now we can interpret what's going on right here. What's going on right here? DC, because when you differentiate DC, the result is 0, right? So it makes a lot of sense. When you just take differentiation, numerical or not, differentiating a constant, the result should be 0, right? This makes sense. The DC gain is 0, according to our calculation. And what else? We all learned that when we differentiate a signal e to the j omega. Let's say if the continuous time is e to the j big omega t, and we take d dt, what do we have? The gain. Differentiation enhances high frequency. 高频的部分被增强。There's enhancement of high frequency when we take the time derivative, right? So the gain should be proportional to the frequency if we want to numerically approximate what's going on in differentiation. Okay? Because in continuous time differentiation, no doubt, there's no doubt this is rigorous. Right? Take the first derivative of a fixed frequency signal, yeah, a signal with a constant frequency, and take its derivative with respect to time, you get this. And that's a gain, right? That's a gain. Or the absolute value of that should be the gain. The absolute value of that should be the gain. 所以, therefore, the gain, what we are trying to approximate, we want to approximate this idea that the gain should be equal to j omega, which is basically omega, okay? Omega is a gain in continuous time. But now, when we go to discrete time, how good is our approximation? How good is our approximation? Is this a good approximation, at least for low frequency range? No? So I said this is nice because now at low frequency, if we talk about like this frequency range, then the gain function almost looks like a straight line. So we're talking about here, right? Therefore, when omega is much less than pi, at small frequency, then 1 over t 2 sine omega divided by 2 is approximately 1 over t 2 times omega divided by 2. Because when omega is small, sine of it is approximately the angle itself. Sine theta approaches theta when theta is small, right? 2 and 2, then further omega divided by big T. And then what is omega divided by big T? That's big omega, right? So don't we have a nice correspondence between discrete time approximation and the continuous time prototype? Okay, so this system is a approximation of differentiation. Right? It's an approximation of trying to estimate velocity when you have displacement, and it's a approximation of trying to derive the current when you have the charge. Yeah, seriously, that's what it is. Okay, it has a very nice frequency response in terms of magnitude. At least as far as magnitude is concerned. Okay, as far as magnitude is concerned, when frequency is small enough, indeed the gain roughly approximates is what should happen in time back in continuous time. Okay, so there are a lot of things to contemplate 所以就常常来凝视一下我们的答案contemplate our results to see if everything makes sense. Yeah. Okay, so I was trying to say that just one last remark to conclude this slide. Okay, if x is displacement, so y is velocity. Okay, if x is the charge on a capacitor, then y is the current flowing out of a capacitor. So this really, seriously, that's a good way for approximating the dynamics. Approximating what's going on when we take take the first derivative of one variable in discrete time. Okay, it's a good approximation. We can call it a numerical differentiator. Yeah. Okay, so with that, let's finish this lecture. The next lecture, which we're also going to begin today, will be about difference equation. And then in solving that, we will use Z transform. And second point is not that important. I'm really fond of this topic, by the way. You can tell I'm really fond of the topic of linear time-invariant systems. I like it so much, so I named myself Linear Time-invariant on both Instagram and last year thread. So you can find me. My name is Linear Time-invariant. Thank you for attention. Right, thank you for your attention. All right, so let's take a break of maybe like 2 minutes to the next lecture. Right. I mean, there are so many people are good DSP engineer, but only I am linear time invariant. Okay, I'm extremely proud of that. Okay, my Facebook account is something else though. Yeah. Don't try to find my Facebook using that. Okay, I have a different ID. So any third users right here?